today is a really important class. So it's unfortunate that it falls on this day when everybody's probably traveling to see their families. But we need to talk about the water worlds and their connection to the earth worlds, which is really quite exciting, interesting. But does anybody have thoughts from last class? Yes?
I thought it was interesting. So I never really thought of like the gas giants not being like entirely gas. I always thought they were just like a ball somehow. But the fact that it was only like, you said that Jupiter was 1/5 actual gas, I thought that was pretty interesting.
Yeah, that's a really new idea. And it makes sense though if you think about compressing something, like compressing a gas, like you get these like dusters or something, right? It's in a liquid form for the most part. It gets even weirder though when you compress it even beyond that. Then you start to get into even more bizarre phases, and we'll talk about those a bit today too, because these Neptunes and so forth they're considered kind of ice giants, but it's not like the kind of ice that you're used to. Ice is a really confusing word once you get outside of water, because it really just means that the molecules don't have a lot of freedom to spin around and do stuff. They're kind of locked into place by the pressure. So it's more like when you pass beyond the liquid phase, you actually get to a point where it's still individual atoms, but they're locked into position. They don't have a lot of freedom. Yeah.
Speaking of pressure, I thought it was interesting hearing about how much pressure there actually is on those planets and like how that environment forces them to act a certain way.
Yeah, it's an intense amount of pressure, right? It's kind of inconceivable in a way, actually. And yeah, so it's going to be really interesting as people start to think about stars the same way, which is what we're dealing with next semester, because they've traditionally been treated like balls of gas, but that doesn't really make sense. And it turns out that those phase relationships come into big importance when you're trying to make sense of light from far, far away, because liquids and gases behave very different when it comes to light emission, very, very different. Yeah, it's kind of bizarre. What else? Yes, Doris.
I thought it was interesting that like possible reason we're not being hit as much with comets is because like the other planets are either like attracting them or like hurting them almost.
Yeah, the big ones. Yeah, Jupiter is kind of like a big magnet for debris. Yeah, that's really important, it seems like, in the story of why Earth got to be how it is, why it's such a magical place for us to exist, and why we don't see it everywhere else too. Yeah.
I'm kind of like, I was kind of confused about liquid metallic hydrogen.
Mm-hmm.
So it's like, because a solid metal, like they have a sea of electrons is what they say. I mean, I guess I just haven't thought about the atomic structure of a metal very much, because like a liquid, like what's kind of the difference in the structure, like, or in the atoms, like when a metal goes from a solid to a liquid?
From a solid to a liquid. Well, okay, the weird thing is, like, when you try to define a metal, like, okay, usually you go from a gas. So if you look at the phase diagram up here for hydrogen, when you're at a reasonable pressure and temperature, like on the left side, you're basically in this gas regime. And then as you increase the pressure, you're going to squeeze it down into a liquid. But stuff gets really weird after that point. You can also cool it off so that it becomes like an ice, like it's kind of frozen, right? But when you get out into this really, really high pressure regime, these like ordinary concepts of solid and liquid kind of start to fall apart in a way. And so I think your question is like, how is it something becomes metallized in a way? And it really asks the question, what is a metal, right? And the funny thing is that metals, if you push on their definition, are also defined by having delocalized electrons in the same sort of way as these highly pressurized gases and stuff. So I think that it comes down to the fact that we don't have a really, first of all, this phase diagram is brand new. Like, people have only been able to move it beyond the far left-hand corner of this in the last, I don't know, 50 years or so. And really in the last 20 years in terms of actually being able to demonstrate in the laboratory, like, and they can only reach these like metallic liquid forms of it for like an instant, basically. They can apply like a pressure for a short amount of time. They can shock it, basically, and produce, you know, the electrical signature of this state. But it's so poorly understood at the end of the day. Now, the reason that it matters is trying to understand the magnetic capabilities of these things, right? So stars, for instance, are incredibly active magnetic systems. They have these incredible patterns on their surface. There's a lot to it that's very difficult to understand. The same with Jupiter, right? It has an enormous magnetic field, and people have a really hard time understanding how that works. But if you have this really compressed hydrogen, then you have the potential for a conductive medium, sort of like we give the explanation with the actual liquid metals under our feet in the form of this kind of magmatic goop, right, in the mantle and in the outer core. The same kind of system could be accomplished differently with high-pressure gases, essentially. I mean, they're not gases. It's just high-pressure atomized elements, right? So hydrogen it's a single element, and that's, I think, why we go with this word gas, because when we think of gases, we think of single elements. But you could also have a metal that's a single element, right? You could have a brick of nickel or something, right? It's a single atom. Yeah, it's weird. I mean, technically, in a metal, we think about the nuclei as being kind of bound in place, and the electrons, I guess, are just sort of swimming around everywhere. But in something like this, it's unclear whether the nuclei are moving around or not. I tend to think that they probably are not. They're probably restricted in their motion too. I don't know. But I don't think I answered your question as well as I could have. But
I mean, I guess, yeah. I mean, it's just kind of a different phase of matter. It's not, but I still like the structure of a solid metal on Earth also confuses me, because they like the electrons can move freely, but they're like the nuclei are just in place. Like,
yeah, I know.
It's confusing.
It is.
Like, why would the electrons go? So it just seems like kind of a behavior of a liquid, with like them being able to move around.
And there's also multiple electrons in these metals, right? I mean, that's the theoretical structure we have here is that there's different shells, right? But yeah, the actual material significance of even what an atom looks like and what the electron means and what it's doing is difficult to grasp. But a lot of these things make a lot of sense if you just treat, like from a schematic accounting standpoint, if you're like, well, the electron's like this little thing that gets handed between atoms. But nobody really thinks that that's what's happening too. Now, what do they think is happening? Nobody really knows. But nobody thinks that there's this little bowling ball of an electron getting passed around. But of course, then things like conductivity become a lot harder to understand beyond that really simplified kind of crutch that people use. So yeah, I understand it's disappointing, but I'm not sure that anybody's even really working on that kind of a question necessarily. They're just like, can we do this thing and what can we use it for? They know how metals behave. I don't think anybody's really too concerned about what the atoms are doing to make them behave that way. I think it's a bit unfortunate, but it doesn't seem to be a technologically necessary piece of the puzzle. So, what other thoughts? Over here on the far right? Come on, guys. Talk to me. Senna, any thoughts?
It's interesting that when the new telescope is made, that our timeline of the universe it shows how like small we have it at.
Yeah. Yeah, I guess we did mention that briefly too. Yeah, the trouble with telling these formation stories is often that the time needed for some of these processes isn't there. And it comes down to the cosmology, which is defined, it seems to be like eternally defined by how far we can see. Every time that we, basically as far as we can see, we think that's kind of the edge of the universe. So people will say that these really distant galaxies and so forth are from the beginning of time, right? The problem is, of course, that the bigger and better telescopes you build, it doesn't seem like there's very different stuff out there. It seems like it's more of the same. So the question then logically becomes, well, are we just seeing further? Are we not actually seeing the beginning of the universe, but really just seeing what our new telescope can show us about the standard universe? It's really tricky, but I do think those timelines are expanding. We deal with that a lot next semester, which matters a lot, especially when it comes to the evolution of planets. You know, the standard story for the formation of these, and you guys probably gleaned a lot of this from your textbook, is that these planets kind of, there's like a big disk of material that's left over from the sun forming, and that the planets kind of condense as droplets out of that, either through some process of core accretion, right, the story that we tell for the rocky planets, which is, let's say, hobbled in some sense because it's very difficult to get pebbles to clump together into boulders. But assuming that there's some way that that can be done, then the gas giants are thought to form first like rocky planets, and then because they're big rocky planets, they grab a lot of the gas and so forth around them. The same thing goes for the ice giants that we're going to talk about today, Neptune and Uranus. It's basically the same story, except maybe they formed a little bit further out because it's colder, so there's going to be more of those more complex molecules, let's say, or more icy-like molecules, so they can swoop that up. But there's serious problems with those formation stories, and I think that's the main thing that I want to explore today with respect to these. I will take you guys on a little tour. What, did I lose? No. I want to take you guys on a little tour of Neptune and Uranus, because I do think that they're interesting and they're peculiar. But the thing that I really think is interesting is their formation story as it relates to the formation of the Earth. And there's been a couple of papers that have come out lately that I want to share with you guys about that I think can kind of tie the whole picture together in a really interesting way. And of course, the difficulty with telling those sort of metamorphic stories of one planet into the next is often the timelines required. You either need a really long time to evaporate something the size that looks like a Neptune or a Jupiter down to its rocky core so that you get a rocky planet, or it has to have some catastrophic changes in its orbit. It needs to all of a sudden be right up next to a star, getting its atmosphere blasted away, and then somehow find its way back to a nice comfy place like the one that we're sitting at today. So, you know, the standard story, the biggest problem with the standard story about these ice giants is that in order to form these balls of cold, complex molecules like we see in Uranus and Neptune, so ammonium and methane and water, in order to form those, you got to be really far away from the sun, basically. The problem with being really far away from the sun at the orbital velocity that disk would be moving at is that something that big and that far away would easily escape the orbit of the solar system that it formed inside of. So what do they call this crisis? I guess it's called gravitational scattering. But the problem is that you need to basically, as soon as you form these things, they have to move interiorly. They need to move towards the sun so that they don't fly off the leash. And there's been a lot of attempts to rescue that idea over the years. But again, it's very troubling how you actually get these things to differentiate, how you get that core to form. Whereas this kind of new paradigm that's emerging, which you won't find in your textbook, but it is starting to appear in different pieces of the literature, that you actually can accrete stuff inside of a big, heavy clump of ice and molecular hydrogen, right? You can actually imagine how something huge and liquidous or icy like a Jupiter or Saturn that's enormous could be scooping up a lot of rock over the ages and would sort of cram all that stuff down into a nice little rocky looking planet inside of it, like a little seed. And so I want to explore that idea a tiny bit more today. So this is a paper that came out in 2022 that was really quite interesting to me. So these guys were looking at all of the, they were focused on one of the most common types of planets that we see in solar systems everywhere, which is, well, two really common types of planets. One is called a super Earth, and one is called a mini Neptune. These are some of the most common planets that we see in exosolar systems. The strange thing that they noticed was that when you plot the size of these planets, you see one peak of the kind of larger variety. So if we look here, this is the planet size relative to Earth. So you see one little peak, a cluster, a bunch of these planets that I find that are of this mini Neptune size. They're smaller than Neptunes, but they're far bigger than Earth. And then you see another variety that's bigger than Earth, but nothing in between, which is really quite odd. Now, we don't have any of either one of these planets in our solar system. We have Neptunes, and we have an Earth. We have some other Rockies. But we don't have any super Earths, and we don't have any many Neptunes, which is really weird. And honestly, it implies that either our solar system has been through some crazy changes that we're unaware of, or it's a complete freak of a situation that just evolved in a very different way than most other solar systems. But what these authors are trying to understand is why there's no why there's nothing between the super Earth and the mini Neptune, because they're very similar in composition, right? You have, on the super Earths, you have usually a thicker atmosphere than we do on Earth here. They're a little bit bigger, but they have very similar complex chemicals to the Neptunes. And the mini Neptunes are very similar, except again, unlike Neptune, they don't have quite as much stuff in their atmosphere. Their core is still a dominant feature. Anyways, the authors are trying to make sense of what happened here. And the explanation that they converge on is that when these planets are, in order for a planet like the mini Neptune in order for a planet like a super Earth to evolve, it has to actually spend some time as a mini Neptune first. And that means that it needs to actually migrate from the colder region where it can form and accumulate all that ice and so forth that we're going to be talking about with Uranus and Neptune. And it needs to get close to the sun and have it essentially blown off by UV radiation by the sun. And so what they conclude is that as planets are transitioning between the Neptune phase and the Earth-like phase, they have to cross over this portion of the solar system where they're essentially crossing the region where you would find in our solar system Jupiter and things like that. And there's probably a lot of collisions that happen between them. So these planets in the mid-range size are actually selected against really quickly. You don't see a lot of these transition planets because as they go through this journey to get close to the sun and then move back away, they're eliminated by collisions, which is, it's an interesting idea. But what's embedded in it that I think is even perhaps more exciting is that these planets are, in some sense, potentially on a continuum between the Earth-like planets and the Neptune-like planets. And that's one of the first, this is a pretty big paper, and it's one of the first places I saw that actually put that out as a legitimate hypothesis for the formation of those. And of course, that ties into our own planet to some extent as well. And they go through and provide the different mechanisms and talk about how this is sort of the proportion of the different pieces in the atmosphere. So water-rich, hydrogen-rich atmosphere, water-like ices, rocky part of the planet. And you see that as it's getting cooked off by the sun, the rocky component tends to become more dominant, right? It starts to look a little bit more like an Earth than it does beforehand when it's a little bit closer to looking like a Neptune. There was also a Nature paper that came out in 2023, so last year, which was trying to explain the production of the oceans in an evolutionary model that was kind of similar. So same sort of story here. They actually imagined the early Earth as having this very thick hydrogen atmosphere that was reacting with the silicate and the rocky core of the Earth, which is basically most of the Earth at this point under this model, the mantle and the rocky portion. We're on a rocky planet. And then as that thing evolved through cooling and different types of condensation reactions, you actually get the precipitation of the ocean and everything like that. So this is actually a similar story to the Neptune story that was told in the other paper. The only difference is that we start here with this molten blob, right, from the core accretion model. And then that somehow grabs a bunch of hydrogen, which condenses down and makes the Earth. They're both evolutionary models, though, which is quite interesting. This also gives us a nice, this thing almost looks like a mini Jupiter because of the hydrogen, the abundance of hydrogen in that story there. So two different evolutionary pathways, one where the Earth-like planets evolve from something that looks like a Neptune, and in this one it looks like the Earth-like planets are the core remainder of something that looked like Jupiter, whose atmosphere essentially evolved into oceans through a condensation reaction. Both of them are kind of intriguing evolutionary models. Thoughts? You guys are a tough audience today. All right. I mean, I guess this is perhaps less than thrilling if you are not acquainted with as well with the standard formation models for these planets, which has them all essentially evolving in more or less in the place where we find them under very different processes, right? Instead, we have a more linear story where planets start off looking very different than they end up looking, and I think I mentioned to you guys that the Soviet story from Oparin has it going even one step farther, where you actually have stars that are cooling and becoming something like hydrogen-rich Jupiter-type planets. And then, of course, those cool even further down to things that look like rocky planets over gazillions of years. So it's an interesting idea. Thoughts? Yeah.
So if the Earth formed this way, would that mean that, or imply that it formed somewhere else and got collected by the sun, and all of our planets in the solar system kind of got collected by a wandering star?
I mean, that's I don't think that it implies that necessarily, but that's a possibility. I mean, it does imply that the planets' their position in orbits must change, right? It implies that, and this is already sort of baked into the standard model because, like I said, even if you form these Neptune-like planets far away, so they're cold enough to condense all of this complex matter, they have to move out of that orbit rather quickly or they'll fly off the leash. So the idea of migrations is kind of pretty standard. The difference being with a lot of these, like with the super-Earth formation model from the mini-Neptune, that you literally have to have a step where it goes from looking like a Neptune to getting cooked down to looking like something like an Earth, and then move into a position, at a nice place where it's not going to continue to get cooked down to something that looks like a Mercury or something like that, right? So it's this just so story of how everything would have to move in just the right ways so that it doesn't get cooked too much. I mean, it's very much like grilling or something, right? You can't you don't want to char everything, but everything has to get cooked just so, which I think makes it difficult. Plus, we don't have a good way of understanding why orbits would change. I think that's the other hard part about this for most planetary scientists and most astronomers to swallow, is that everything seems really stable right now. All of our orbits are in different forms of resonance with one another, which seems to stabilize them. And if that is something that isn't as stable as it seems, that's a really unsettling realization too, in some sense, because our existence depends on our orbit being stable. I've mentioned several times that there's this very bizarre phase of Earth's geologic past called the snowball Earth, where the whole Earth was completely frozen over, and nobody really knows why. Of course, I keep saying orbitals, like atoms. If the orbits are changing, then you have the opportunity maybe for a rocky Earth-like planet to end up in a colder region for a prolonged period of time. But what causes the orbits to all of a sudden shift? And what causes them to shift in a way that's stable? Like, why don't they just all fly off the leash if it changes? Like, there's something about that process that happens so infrequently that we can't study it, that most people would probably prefer to ignore that it's even part of the story. It's also just so disturbing to think that one day Earth won't be in the same place in its orbit that it's been for millions and millions of years. Did that answer your question to some extent?
So, okay, when you mentioned the snowball Earth, do you mean the Ice Age?
No. This is something very different. So this is funny. Ice Age, glaciation, snowball Earth are actually all different ideas. Colloquially, so when people on the streets say Ice Age, they usually mean the last glaciation, or the glacial maximum. Technically speaking, the Ice Age is something we are living in right now, which is the period for the last, I don't know, I want to say million, maybe a couple million years. I'd have to look that up. But during which the Earth has been going through this alternating phase every, I don't know, 100,000 years or so, where it goes from being completely, the polar caps have huge glaciers, and then they don't, and then they do, and then they don't. That's only been going on for a little while. And so that period of Earth's history we call the Ice Age. But people on the street generally mean the last time that we had huge glaciers at the poles. Snowball Earth is a singular event that occurred once, I don't know, I think more than 1 billion years ago, a very long time ago. And the entire Earth was covered in like 5 miles of glaciers, which is really weird because even during the glacial maximum, back maybe 15,000 years ago, the glaciers only reached down into, about Wisconsin or something like that. So they're big, but they don't cover the whole Earth. This snowball Earth thing was a really weird one-off event. And it's difficult to explain that using traditional mechanisms. People have tried with like crazy volcanism or something, but there doesn't really seem to be obvious traces of that. It's a very difficult one to explain, which is why I think like the orbit shift would be an interesting explanation for it. But if you did have an orbit shift, then it obviously restabilized in such a way that it came back into a more temperate climate, such that all the complex life that we're used to could evolve. That was, I believe, that was after life appeared on Earth, though, that snowball Earth. So now not complex like birds and mammals and things like that. Those are much, much more recent. But it seems like some sort of little microbes and stuff survived underneath all those glaciers, which I think is why people are so hopeful that when they go to these moons of Jupiter, like Europa and Enceladus, that despite the fact they're covered in ice, there might still be critters living down beneath the ice, because it seems to have happened in our past too. So, weird.
How long was the snowball Earth period?
That's a really good question. How long did snowball Earth last? Millions of years, it looks like. The cryogenic period, roughly from 640 to 710 million years ago. So like 100 million years, looks like. Almost. No, not quite. 50 million years, a really long time. Yeah, cold period. Very bizarre. And I guess this occurred, like I said, about 700 million years ago. It's a long time before, like way before dinosaurs or anything like that. It was probably just microbes and little algae-like critters and stuff like that. So that was a weird one-off period. And I think it's just going to be very difficult, even if we're able to observe other exoplanetary systems, if these orbital repatternings are hundreds of millions of years apart, it's unlikely we're ever going to observe anything like that happening. The timescales are just off the table. So it makes it very, very tricky to explain. I mean, ultimately, the stories we're trying to tell are just, I like to like just recenter how preposterous it is to try to tell a story about something that happened 600 million years ago. Like, good luck like telling a story about, with precise detail about what happened a month ago in your own life, based on the evidence that remains. Yeah.
How long will it be before we get to like go to one of those ones and see if there's?
That's a good question. I think that pretty soon. So there's a couple of, you're talking about the Jupiters, like frozen moons? Yeah. There's 2 missions that are underway right now that are surveying the area. They're actually going to orbit Jupiter. They're not even going to orbit the moons themselves. But they are part of a wider program whose next step involves robotic, probably involves orbital exploration of the moons and then robotic landing, drilling down through the ice, which is tens of kilometers thick. So that's a real interesting trick too, is how do you even get through that? The best ideas are something like make a little nuclear furnace and just set it on the ice and just let it kind of melt its way down. There's also some cracks in that ice too, and Enceladus in particular, you can actually see these geysers of stuff streaming out of the, it's like just kind of gushing out, just like Old Faithful or something like that. They're really, really quite incredible. I actually think we'll have some time next class to go through these moons a little bit deeper, and we'll take a look at that. But yeah, we're on our way, and we're hopeful. So I don't know if there'll be critters there or not, but if we could find one of these geysers, maybe we wouldn't have to drill down. Maybe we could taste them, chemically speaking, and see what's up. See if we can see any signs of what's going on below. But strange, this icy sub-ocean seems to be pretty common in our solar system, actually. Very weird stuff. All right, any more thoughts on this formation paradigm stuff? Yeah. All right. Let me know if you are struck by thoughts as we move on. Let's take a little tour of our 2 ice giants, Uranus and Neptune. So again, this concept of ice, it refers to these volatile chemical compounds that have freezing points around 100 Kelvin, which is quite cold. But this is like, generally speaking, when we say ice giants, we really just mean stuff that's made out of water, ammonia, methane, and stuff that is kind of freezing anywhere between where our water ice freezes and down below that. So people, really struggled with the composition of these planets until quite recently. I think it wasn't until the 1990s that people actually decided to classify Uranus and Neptune as a different form of planet than Jupiter and Saturn, because they weren't dominated by the same simple elements like hydrogen and helium, although they still have a lot of that too. And these things orbit really, really far away. Let's see if you guys can see here. Here it comes. Oops, coming around the side. This is kind of very difficult to see on this screen. I'm sorry, I got a better one here. So we got Pluto's the purple guy way out there. Otherwise, we see Neptune and Uranus. Now, there's also, these planets are not really visible with the naked eye. So these are also relatively new to people's even interest in them, because nobody really cared about them for thousands of years like they did with all the other planets that we've been talking about. So, okay, yes, here we go. If we look at a cross-section of these giants, what do we see here? They're primarily composed of these heavier elements, like I said. We see oxygen, carbon, nitrogen, sulfur. They also do have a fair amount of hydrogen in their envelopes too, so they have a little bit of that gray. If we can zoom in on them, there's a bit of the same stuff that we would expect in the Saturns and Jupiters, but it's just in the outer atmosphere of them. Otherwise, we go down and we actually start seeing methanes and water and ammonia, right? The mantles of these planets is actually more composed of that kind of stuff. All right. We'll keep going. There's something also that's really bizarre about these. So I think understanding the phase diagrams, like you were mentioning earlier, is really important because the magnetic properties of these planets is really, really bizarre. So when we look at something like the Earth, or Jupiter even for that matter, we see that the magnetic axis is tightly correlated with the spin axis of the planet, which that works out really nicely with the story that we were telling about how that magnetic field is produced. These guys are really, really weird. So if you look at this black bar, that's showing you the spin axis of these planets. And if you compare them to Earth, you can see our spin axis and our magnetic pole are pretty much in the same vicinity. And of course, our magnetic pole is moving ever so slightly. But these guys are completely bananas. Actually, Uranus's spin axis is turned on its side, which is really, really weird, right? Like, why is the thing not spinning in the same plane as most of the other planets in the solar system, and in particular as the sun, which is what you would kind of expect if the thing had just been more or less born as it is, right? Something somewhat catastrophic appears to have happened to this guy at some point in its story. But even more bizarre is that the magnetic axis doesn't correlate with the spin axis. So there must be some other process going into the production of that magnetic field that's different than the one that we're traditionally used to with the Earth, for instance. Unless, of course, that at the center of Uranus is a very Earth-like thing who has a spin which is actually correlated with its magnetic axis, right? So you can imagine that guy stuck at the center of that guy, and for whatever reason, it just hasn't gyroscopically put itself into place because this tilt business that it exhibits at this point happened in the relatively recent past. Either way, it's a kind of phenomenal mystery. Neptune seems to have a similar situation going on, a little bit less severe, 47-degree difference, and Neptune seems to have righted itself a little bit with respect to the ecliptic. It's spinning closer to a proper orientation, but not exactly. So a lot of mysteries there. They're very strong magnetic fields too, so even if the core of these planets, being an Earth-like object, is in some sense responsible for a large part of the magnetic field, it can't be the whole story necessarily because their magnetic moments are something between like 20 and 50 times as strong as the Earth's. So there's something being amplified in that by the outer goop, whatever you want to call it, the outer ices stuff. Questions, thoughts? Yes.
So with Earth, like the magnetic poles kind of like the line for that goes like straight through, and it's it connects very well right in the middle of the circle, whereas like Uranus and Neptune, like they're like, especially Uranus, it's like a third of it versus 2/3.
Yeah, I never noticed that before. That's a really good point. I wonder if that's accurate. That's very, very bizarre. Wow, yeah. You know, it's kind of frustrating because I think so very little is known about, like, so very little empirically can be said about what is happening beneath the cloudy surface of these planets. But the way that it's drawn right there, and I'm not sure if that's an artifact of this illustration, I doubt it. There must be something to that. That's really fascinating. But perhaps you could imagine that the core is even like lopsided to some extent, right? If the core is the source of the magnetic moments, it's still unclear. But yeah, we obviously can't land on these planets, and so we can't do any kind of easy like seismographic studies, which is how we know anything about our own core, is through these kind of reflection studies of actual sound waves in the material. Right? The same with the moons. So we have a pretty good sense of our own internal onion layers in the moons as well. But with these things, it's a little bit sketchier. I don't think we just know any certainty what's going on underneath them. The only reason that they suspect that they have a core at all is just from the density estimates, right? It's like, well, it's a little bit too heavy not to, essentially, given how wide it is, and given how obviously not dense its upper atmosphere is. So it must have a core. And so, yeah, even that is tenuous and hypothetical. All of this, these stories have to be strung together on a very few facts at some point. I think almost everything we know about Uranus and Neptune empirically is derived just from looking at it and from, I believe it was Voyager 2. I'll dig that up in a second, but we've basically only been by there once from what I can tell. So very scant primary data on these things. All right. All right, so let's talk a little bit about Uranus first. So Uranus, seventh planet from the sun, worth remembering. It has the third largest radius and the fourth largest mass in the solar system. It's also the coldest atmosphere in the solar system. So its temperature on average, its minimum average temperature is something like minus 371 degrees Fahrenheit, which is really, really cold. Now, I guess Uranus is technically visible to the naked eye, but it was never really taken serious. I think it's very difficult to see. I've actually never seen it before, and I often look, and I see it on my Star Finder app thing, but I can't see it. So, some people say it is visible, but for whatever reason, the ancients did not care about it and did not pay much attention to it. It also orbits really, really slowly. I think that it takes many decades for the thing to go around the sun, so perhaps the fact that it wasn't moving that fast and it's really dim, nobody paid attention to it. Kind of an interesting mythology associated with Uranus in a sort of terrifying way. Does anybody know the story of Uranus and Saturn? Yeah?
Well, like Uranus and Rhea Gaia. Rhea is one of the Titans. They're the parents of the Titans. So like everything came from chaos, and then Uranus just happened, and then they're the parents of the Titans. I actually don't remember the rest of the story besides chaos and the Titans.
Yeah. So
There's something weird with like them eating him or like something like that.
yeah, I'm not super familiar with it, but from what I've read, so the Roman version of this is Caelus, I believe, which is the primitive god of the sky. The Greek, Uranus was the Greek version, or maybe I have it backwards. No, I think I have it backwards. Uranus was the Latin version. It comes down to the myth of Saturn, which was Cronus, I believe, in Greek. It's funny how the Romans just kind of seem to be just a different ethnic version of the same Greek stories at the end of the day. Different language, but very similar. But I guess the story goes that Saturn was the son of Uranus, the sky god. So Cronus was the son of the father Uranus, and Saturn castrated his father Uranus and threw his genitals on the sea, which led to the birth of Venus. That's a pretty gnarly myth right there. I'm like, that's a very, very strange thing to say. I was trying to make sense of what in the world that could possibly mean. There's something about order, though, right? So Saturn, Cronus, is putting order on the sky to some extent. And in doing so, sort of takes the power away from the chaos of the sky. That's about as far as I could get with it. Yeah, please, take your stab at it.
Both names of each one.
Yeah. So Cronus, this is like time in order, is Saturn, who is the son of the sky deity, which is Uranus / Caelus. And Saturn, Cronus, castrates his sky god father, Uranus. So the sky god gets castrated by time and order. Oops. What do you guys make of that? Anybody? Yeah.
Well, my first thought is like, kind of like Hamlet, killing his father, and obviously we're not left with such a great ending as like the birth of Venus in that story. But I do like the idea that like, or like it makes me think of like cutting like epigenetic patterns of like pain, and like by doing that there's this like new beginning, this renaissance of like a goddess that we can worship that represents something better. But I don't know how to put that in terms of like time and
Yeah, I think you're onto something with that, actually. I mean, Venus kind of represents like love, like almost like romantic love too, right? There's something about, I think that
and like free love.
y-
Not like not constricted by like just just like whatever kind of love is necessary to continue your bloodline.
yeah, something reproductive about it, I think, in that sense, right? Just to be like very on the nose about it. It's very, yeah, there's like a lust element or something to the Venus stories. Yeah, it almost feels like, okay, so I think of Cronus as being human, the spirit of humans trying to put order onto things and trying to sort of orchestrate their lives. So like in a primitive state, if we're all just, I don't know, a bunch of amoebas or something, but like say before humans were humans, but we were some sort of like ape of some sort, things would just unfold. Like if you guys have like cats or spend a lot of time with animals, like they sort of just act instinctively and stuff. They don't actually put a lot of obvious thoughts into ordering their lives around them, right? Like they're not necessarily constructing. It gets hard. It gets really hard here. But I think that there is a step at which humanity supersedes a lot of other animals and that we apply a lot of order. And time is the principal mechanism by which we do that, I think. So time, by saying, like, this pattern of night and day is predictable, we can chop it up into smaller subunits, and then we can start deciding when, all of a sudden, we're going to do certain things. We're all going to meet over here and go and attack this other tribe, or we're going to meet over here to do this harvest every year, or we can actually start to organize ourselves on the basis of recognizing the cycles of time. And so time is kind of like this central organizing feature. And in the same way that I think that like reproduction and mating would happen in an unorganized society, it would have just kind of been taken, probably would have not really been controlled or patterned in any particular way. I think that when you start to order life according to time, then you also have the ability to decide when to have children, like when to time all of these things, right? So like humans are, by the way, I think we might have talked about this before, but humans are really weird because human women, you cannot actually tell when they are fertile just by looking at them in a picture. But almost every other mammal you can, especially primates, they're really obvious when the females are fertile. They have changes in the color of their skin, all sorts of stuff. And so there's something really weird about that with human beings. It's actually something of a secret, right? But it can be timed, actually, right? You can actually time fertility cycles so that you can, if you want to, get pregnant, or not if you don't want to. And there's something about that power of being able to time that stuff. And I think that it's no coincidence, although it's hotly debated, that the length of the lunar month is almost identical to the average length of the female fertility cycle. So there's probably some timing going into that stuff, yeah.
Well, okay, since we originally talked about that in class.
Yeah.
The first class.
Yeah.
I looked more into that, and so my thought was kind of like, it could have to do with nomadic people, like ancient humans, like living nomadically, like and then.
Explain that.
migrating with the
Okay.
moon. So it's like, they're migrating, I don't know if ancient humans tended to stay in one place or if a lot of them were nomads.
Probably both, yeah.
But like, they would, like, or if they would travel, so it's kind of up in the air. I don't know if they would travel by night necessarily or things like that and need the moon to navigate, but if they were using the moon for navigation and they were like,
Certainly for time, I think.
yeah, so for time and like, and then they would settle down and live a certain place. So I think that could have to do with mating cycles, like the different times that they would move around would correlate with the moon, and then that could have evolved like in that way. But it's also like, so I think that like on its face like would seem like kind of how like menstruation would be aligned with the moon. But I also like, I've heard that like ancient women did not have as many periods as they do now.
Oh, I never heard that.
Been like, it was like much further apart,
Huh.
or they were much older, or like, I mean, usually menopause would be at a similar age. Well, they would die sooner, but like,
For sure, yeah.
but they wouldn't start their period until they were like 18.
It does seem to be receding in the modern
Yeah.
society.
And that could also be like nutritional.
Yeah.
Having a consistent
Plastics.
nutrition
Yeah.
definitely like, I mean, in like with the war too, like anyway, like in times of war, there would be adolescent girls that would start their periods much later because of food shortages. But it's also like, I've heard this and I need to look into it a little bit more to like see if it's accurate, but they would only menstruate like 50 times in their lives, and now it's like 400 times.
Wow.
And it's not necessarily.
I wonder if they'd even know that, though. Yeah.
Yeah, so I do kind of have to like verify that, but like, I don't know, it might have been a much longer cycle than it is currently.
What were you saying?
Oh, I was just saying like with like a grain of salt.
Yeah, of course.
But like, so it may not have always been in line with the moon, and then it's just kind of a strange coincidence. I don't know.
Yeah.
When the moon was like closer to the Earth, how long did it take to?
I don't know how long ago that was or how much closer it was. That's also a very difficult thing that needs to be taken with a grain of salt. I don't know how. The thing is, if the moon still goes around the Earth at the same rate, it's very difficult to say when it was closer or not closer, right? 'Cause it's easy to tell by the tides in the archaeological record, where how long the day was or how long the lunar day, the lunar month was. But in terms of like the absolute distance, that's very tricky. Did you have a thought?
I did, but I don't know.
Like,
I'm not too sure why we would get.
Oh, yeah.
Why like there would be more frequent periods, but for like in the case of women during war and their period cycles are like farther between, that has to do a lot with stress. 'Cause
Oh yeah.
with stress, it stops from certain bodily functions from happening, and then your mood and all these other things changes, so your cycle is not as often as it would be.
Yeah, all this stuff is actually like really poorly studied. There was one really big Nature paper that came out in the 70s, I believe, that some researcher made this case that women's cycles would sync up if they were isolated together. And then all these people like refuted it with these other papers like, no, it's not true. But I don't know, I've heard like anecdotes too, like I have a friend who, a friend of a friend, my wife's friend actually, who like hiked the PCT, and she said that when she was traveling with like groups of women that this would happen actually, when they were kind of away from cities and just all together, like they would actually end up completely cycling exactly together. I just find it to be a really astounding coincidence that like the average length of a menstrual cycle is almost identical to the length of the moon's month. I mean, it could just be a coincidence. That's totally possible, but it's pretty bizarre too at the same time. And so I can't help but thinking that in some sense it served as a primitive clock. Plus you have to marry that to the fact that humans are the only primates where you can't tell if the women are reproductively receptive, right? That's really, really, it's hard to like overstate how weird that is in the animal kingdom. You almost always can tell by looking at an animal whether it's fertile or not. It's in that phase of its cycle. You can't tell with humans though, so they had to have some external, something evolutionary that humans did differently with that, where they were actually able to take control, I think. I think that it was about taking control. So like, you don't necessarily want everyone to know when you're fertile. You want to be in control of it as a woman, actually. And so you have that knowledge and you're able to time it, perhaps using like the celestial, or maybe you just count days. I have no idea. You know, it's funny because like not for all women, but for a lot of women, this cycle is very, very predictable, actually, right? And so you can actually plot out when you can get pregnant versus when you can't, right? And this is, you know, of course, in our modern age, like you take like sex ed or something in high school, like they're all like, well, you can, you know, take control of your reproductive health by, or whatever, your decision to get pregnant or not through like birth control pills, like, you know, different protections like that. But the truth of the matter is you can, for the most part, most women can actually plot out exactly on a very regular basis how many days it is between these moments, which is really fascinating. So anyways, I wonder if there's something embedded in this mythology about that whole process, because I think these myths in some sense reflect this ancient memory of what it meant to become humans as opposed to just being these kind of apes. You know, there's a really, if you look at the history of humanity, we've had the same anatomical shape, like our brain size and our muscles and skeletons are like basically the same as they've been for like 1,000,000 years. But humans, in the way that we think of ourselves, you know, sitting in this classroom and behaving the way that we behave, and all of the peculiarities of how we govern our reproduction and our, you know, the concept of human rights and civilization and all of this, this is so relatively recent. Like it happened, you know, you might be able to say it happened like 50,000 years ago, maybe. Maybe you push it back 100 because you find some evidence of like burials or ceremonial activities or something. But it's really, really recent compared to how long our bodies have looked like this. And so I feel like there must be some memory of the moment when we decided, when we had this sort of self-awareness to start thinking in this new way that's so characteristic of what it means to be a human being, this self-awareness. And so I feel like this myth is in some sense pointing to part of that process. I don't know, just a guess. But yeah, any final thoughts about that? The mythology? All right. Well, we can get back to it. What do we want to say? Like I said, yeah, it was Voyager 2. So 1986 is the only time that we ever made a close-up investigation of Uranus. So, you know, this is usually the point in this class where we're getting so far away from the planets that we've actually studied up close that it becomes very, very difficult to piece together any story. These are also two of the most bizarre planets just from their spin tilts and their separation of their magnetic axes. They're just very, very weird things, right? This is the path of Voyager 2 as it traveled out to the edges of the solar system. You know, they considered, maybe you guys remember, there was a Saturn mission recently called Cassini. They actually ended up crashing the probe into Saturn and got a bunch of really good pics of it and stuff. There was a big debate at NASA as to whether they should send that probe on and check out Uranus instead, but they decided to crash it into Saturn at the last minute. Yeah.
Did we ever get that back?
No, that's it, and it got gobbled up. It just crashed right into the atmosphere, and that was it. I mean, it's probably part of the core now. Yeah. What else can we say? Uranus actually has also, you know, adding to this bizarre, complicated history of it, you know, it's turned on its side. That's really weird. Its magnetic moment is separated. It also has the highest eccentricity of any planet. So it's a really long elliptical orbit. it's the difference between its minimum and maximum distance from the sun is almost twice our distance to the sun. So it's a really oblong orbit, adding even more mystery to the story of its past. Let's see, 84 years it takes to go around the sun, too. So be lucky if we see it go around once. All right, so let's, it's about 4, this is interesting. I like looking at them side by side. It's bigger than the Earth, but it's not that much bigger. It's only about 4 times the radius. But its mass is about 14 times ours here on Earth, which probably isn't as much as you would expect it to be, but you got to remember, this is part of the reason we think that it has a core at the center of it, because it's a bit too big to be explained as a sort of homogeneous ball otherwise. And it's actually as a result of that, if you do those calculations, you come out with the fact that the thing's average density is like 1.27 grams per centimeter cubed, which makes it the second least dense planet after Saturn, which is kind of interesting. Uranus is interesting. It actually, despite being, and this is where things get kind of bizarre, despite being technically, well, despite us calling it an ice giant, it actually radiates out about the same amount of heat that it gets from the sun on balance, which is interesting because Neptune, which is the other side of this story, and we don't need to talk too much about Neptune right now because it's basically the same story as Uranus. Neptune actually radiates out like 2.5 times the heat and radiation that it gets from the sun. So there's some sort of internal process by which these guys generate warmth, and that's not very well understood at all, especially since they don't seem to have like the mass for the compression to accomplish it by itself. Now, an argument can be made that it's leftover heat from when it was a much bigger, hotter object, or early on in its formation, but nobody really knows for sure. What else can we say? Its atmosphere is, it's got a sort of thin atmosphere, like we said, that's very similar to Jupiter or Saturn. It's this molecular hydrogen and helium. The blue color, of course, comes a little bit lower down, which is methane, actually, which has this nice absorption band in the visible and near IR, which gives it that kind of cyan color. We also find in the atmosphere traces of complex molecules, which is kind of interesting. So actual hydrocarbons, which is, I think, was really shocking when this was figured out, because when I was a kid, hydrocarbons were referred to almost exclusively as fossil fuels, right? So we thought that the way that all hydrocarbons were produced was through biological processes, right? The decay, decomposition, pressurization of biological materials. That turns out to not be the case, and as we go out, as we start looking at some of the moons, we're going to find tremendous amounts of methane and hydrocarbons, huge lakes of hydrocarbons on Titan, which is a moon that we'll talk about next time. So really complex, I mean, C2H6, ethane, acetylene, C2H2, methylacetylene, just really complex hydrocarbons out there, which is interesting. I mean, all right, take care.
Thank you.
Yep, see ya. Which is really interesting because you've got to start thinking that in some sense the production of these like more complex chemical elements, yeah, it's interesting on its face. Like the standard explanation is that it must have accumulated these after its formation. But also just if you think about it on a metamorphic timeline, the cooling and condensation reactions necessary as you go from something that's more big, like a Jupiter, that's very simple elements, and it cools and condenses, and it actually has interactions with carbons, and it's actually able to start to cool and produce some of these complex elements. You might be able to even put these ice giants on a similar continuum evolutionarily with the big Jovians. All right, I really want to talk about, I think I'm going to talk about the moons next time, because they're probably the most interesting piece of the whole puzzle with both these planets. I'm going to skip most of Neptune because it's basically the exact same story that that we can tell about this one. Let's pick up next time with the moons and see if we can't put together a story of where they came from in this whole process. But otherwise, yeah, I think we'll just stop early today and let you guys get on with your Thanksgiving break. And yeah, if you're traveling, travel safe. I hope you guys have a good time with your families. And we will wrap up this whole class next week. We only got 2 more classes, so let's do it.